Artist Boat, and today we are over in the west end of Galveston Bay, and we're going to take some water quality measurements that we would take on Artist Boat's Eco Art Kayak Adventures. Today we're going to be measuring stuff like the temperature of the water, salinity, turbidity, nitrate level, and also dissolved oxygen and pH. So we are over on the west end of Galveston Bay in a cove called Starvation Cove. So we're going to go ahead and take a look at a map and see exactly where we're located.
For Artist Boat Adventures, we launch on a boat channel adjacent to the Coastal Heritage Preserve, and that ends at Starvation Cove. We are currently standing at the place noted as Science Stop on the map. Let's zoom out just a bit more and notice where Starvation Cove is located in the West Bay.
So the first thing that we're going to measure today is the temperature of the water, but I do have to first get my water sample. So y'all join me down by the water and we're going to collect our first water sample. The reason why we care about what the temperature of the water is because it's going to affect the marine organisms living within the bay. Some species tolerate warmer temperatures, some tolerate cooler temperatures. It's also going to be an indicator of when they can start some biological processes. So it's just really important to know what the temperature is. So as we're taking it, what I'm going to do is I'm going to put my thermometer in my bucket, and I want to put it about in the center, and I don't want to hold it too close to the top so it's not affected by sunlight, and I don't want to hold it too close to the bottom. So I'll put it in there, and then we wait for 30 seconds. So keep in mind that the temperature is always changing. It's not going to be the same day to day. It can even change within 24 hours. Alright, so now that we've waited 30 seconds, we're going to go ahead and take our measurement. And it is at 18 degrees Celsius. So you might be wondering why we're using Celsius today instead of Fahrenheit, and that's because a lot of other countries other than the US uses degrees Celsius, and also scientists. The science community uses Celsius and the metric system. So that's how we're going to measure it today. If we were to record this data, then other scientists and people around the world can see that in the west end of Galveston Bay today that our temperature was 18 degrees Celsius. And that's about equal to 60 degrees Fahrenheit, in case you were wondering. But we're actually not finished yet. In science, we always want to do our measurement more than once. There could be errors that happen because of me or something that we did wrong. So we want to do it 3 times and then take the average of those 3 measurements. So we're going to do it 2 more times. So we took our measurement 3 times. We got 18 degrees Celsius, 18 degrees Celsius, and 19 degrees Celsius. So if we take an average of that, it's about 18.3 degrees Celsius for the west end of Galveston Bay today. Alright, so today we're going to be measuring what the salinity of the water is. Salinity is a measure of how much dissolved salt is in the water. So with the west end of Galveston Bay here, we have what's called brackish water. And brackish water is a mixture between fresh and salt water. The fresh water is coming from the San Jacinto and the Trinity River, which empty into the northern part of Galveston Bay. And the salt water is coming from the Gulf of Mexico. So in this estuary environment where the rivers are meeting the ocean, those 2 types of water are mixing together to create brackish water. Now with anything that you're measuring, like the salinity, we have to have units. If I was to measure the length of my arm, the units that I would use probably would be feet or inches, but with salinity, our units are a lot different. It's called parts per thousand, which is kind of a lot to say every time, so I'm going to shorten it to just 3 letters, PPT. So it's kind of like a fraction. It's like saying I have this many parts of salt per 1,000 parts of water. Now freshwater salinity is anywhere between 0 to 5 ppt. So at the most, it would be about, let's say, 5 gallons of salt per 1,000 gallons of water. Salt water, on the other hand, on the other end of the scale, is an average of 25 to 35 parts per thousand, which might not seem like a lot, but some of you may have been swimming at the beach and accidentally swallowed some of that salt water, and it tastes pretty salty, right? So brackish water is anything that's going to be in between. It can be about 6 parts per thousand to 24 parts per thousand. And it's always changing the salinity here. So let's go ahead and measure and see what the salinity is today. Alright, so to measure our salinity, we're using this really cool instrument called a refractometer. And the reason why it's called a refractometer is that it's measuring the angle of refracted light off of our sample today. So I'm going to go ahead and get a sample on this little blue window that you see here. And then I'm going to be really careful to close my lid, and I'm able to look through my refractometer to take my reading. So when I do that, I'm going to see a darker blue color on top and white on bottom. And where those two colors meet, I'm going to look over to the right and read on my scale. It goes from 0 to 100 parts per thousand, and we'll see what it is today. So I have my water sample on the end of the refractometer. I'm going to go ahead and take a look. Sometimes I have to give a little bit of shade so that I can see it better. And I am reading our salinity at about 25 parts per thousand. You might be thinking that's a little bit closer to that saltwater range, but think about where we're located today. On this end of Galveston Bay, we are really close to our saltwater source, so we're closer to the Gulf of Mexico, and that's why we're reading that high of a salinity today. So remember, I had to take this measurement a total of 3 times to get my average, and we found that there's an average of 25 parts per thousand for the west end of Galveston Bay today. But keep in mind, in Galveston Bay, it's not all the same salinity in every part of the bay. Think about those freshwater rivers that are emptying into Galveston Bay. In the north part, we typically see a salinity of about 0 to 5 parts per thousand. In the center of Galveston Bay, we typically see about 10 to 15 parts per thousand. And in the West Bay, we see anywhere between 20 to 25 parts per thousand usually. And other than location, there's a lot of other factors that can affect the salinity, like rainfall. We're getting a little bit of rainfall here today. That extra fresh water is going to actually cause the salinity to go down when you're adding more fresh water. So if we were to have something like a huge rainstorm come through, or even a hurricane, that can cause the salinity to drop really quickly. An example of that is Hurricane Harvey. So in 2017, Hurricane Harvey dropped trillions of gallons of water on Galveston Bay, and that caused the salinity of the west end to plummet to about 9 parts per thousand. So that can actually affect some of the marine organisms that are living out here, such as oysters. They can't just pick up their shell and scoot away from where the salinity is lower to somewhere where it's more favorable. Oysters really like brackish water, which is about 15 parts per thousand. So 2017, they really suffered having 9 parts per thousand for an extended period of time. So marine organisms can really suffer when the salinity changes. So that's why it's important to know what the salinity is of the bay. The thing that we're going to measure is the turbidity of the bay, and turbidity is a measure of the clarity of the water in relation to how much suspended solids are in the water, and that includes the sediment and sand that's on the bottom, and when it gets kicked up in the water, it's going to make it a lot less clear and harder to see through. So you may have been to places like Florida or the Caribbean where they have really white sandy beaches, but the water is also really blue and clear. And that's not really what we see in Galveston Bay, but there's a reason for that. Our sediment here is really, really fine particles. So it takes a lot less wave energy to kick up that sand and sediment in the water to cause it to be a lot more turbid and less clear. And in places like Florida and the Caribbean, their sand particles are a little bit bigger, so it takes more wave energy to kick them up and to cause the water to be turbid. So to measure the turbidity today, we're using what's called a turbidity tube. So what we're going to do is fill this tube with water. But before we do that, I want you guys to take a look at the disc down here at the bottom of the tube. This black and white disc is called a Secchi disc. So that's going to help us with measuring the turbidity today. And it's the perfect instrument for using in a shallow water environment like we're in today. So I have my assistant Grace with me. She's going to help me measure the turbidity of the water. And what we're going to do is take our sample here and we're going to pour it in the tube. We're going to look through the top and see if we can see the Secchi disc at the bottom. So I'm going to go ahead and pour my sample in our tube. And sometimes we miss the tube a little bit and don't get it all in there, but that's okay. All right, so now we're going to see if we can see the Secchi disc from the top of the tube. So we're looking for that black and white disc at the bottom, and currently I cannot see it. Can you see the Secchi disc? So what we're doing now is we've started the flow of water, and I'm going to look through the top of the turbidity tube and see when I can barely start to see the disc. Go ahead and stop. So when I barely start to see where the black and the white meet, that's where we're going to take our reading. Alright, so now can you see the Secchi disc at the bottom? So now we can take our measurement on our turbidity, and on our tube we actually have it in centimeters. Remember, we're using the metric system today, and I have just a little bit above 40 centimeters. So what this means is if the water was any deeper than this, we wouldn't be able to see the tops of our feet when walking through the water. So the reason why we care about the turbidity of the bay is that if there are high levels of turbidity for extended periods of time, it can actually block sunlight from reaching aquatic plants, which would keep them from photosynthesizing. It can also end up smothering marine organisms, and bacteria and pathogens can attach themselves to the sediment in the water column. So now we're going to measure the dissolved oxygen in the water, and dissolved oxygen is oxygen that is in the water. And we know oxygen is important to support marine life because fish also need oxygen to be able to breathe. And our dissolved oxygen is really closely tied to the temperature of the water, and it's temperature dependent, which means the amount of oxygen can change when the temperature changes. So to understand this, we have to think about water kind of on a molecular scale. So water molecules, or H2O, is made up of 2 hydrogen atoms and 1 oxygen atom. So when the water is really hot, the water molecules have a lot more energy, so they're moving around a lot more and bouncing around, and that can actually cause oxygen to come out of the water. So hot water has less oxygen. In cold water, water molecules have less energy, so they move a lot slower and they stay closer together. So cold water can hold more oxygen. So we're going to go ahead and measure with my dissolved oxygen kit how much oxygen is in the water today. So to measure the dissolved oxygen today, we're actually going to see a chemical reaction. And the reason why I know it's a chemical reaction is because we're going to see a really awesome color change. So y'all go ahead and join me in seeing how this process works. So the first thing that I have to do is get a small sample of my water sample, and I have to fill this cup to the 25 milliliter mark. So I'm going to go ahead and get my sample, but I see that I'm over 25 milliliters. So one really cool thing that I can do is hold the cup in one hand and hit it with my finger with the other and kind of tap that out. Instead of just pouring my sample out, I might pour too much. So now I have 25 milliliters of water. So now what I'm going to do is I'm going to take my ampule, which is a vacuum sealed tube, and it has my reaction liquid in it. And it has indigo carmine, so this is what's going to cause that color change that we see. So what I do is I put my ampule into our sample cup, into one of these grooves at the bottom. And what I'm going to do is pull it to the side, so you're going to hear a snap, and that's the tip of the ampule breaking, and now it is filled all the way to the top with our sample. So now I'm left with a bubble at the top, and I can actually use this bubble for mixing. So I'm going to invert it 3 times so that I can mix my reaction liquid with my sample. And then we have to wait about 2 minutes to see the full reaction. So remember, we get to see a really cool color change with measuring our dissolved oxygen. So I have this comparator here that's going to help me measure how much oxygen is in the water. What I do is I just put my ampule in between, and I compare the color, and I see where my dissolved oxygen lies, and I think it's somewhere around a 7. Now remember, we have to have units for whatever we're measuring, and for dissolved oxygen, our units are parts per million, which is very similar to salinity with the parts per 1,000, but for this one, we're gonna see about 7 milligrams of oxygen per 1 million liters of water. So that might not seem like a lot of oxygen, but it's actually a really good amount for the marine organisms living in this area. That's enough oxygen to support them, for them to be able to breathe and to live. And there are some things that can cause the level of oxygen to deplete in the water. So we'll discuss that when we're measuring our nitrate. So how can we tell if the level of dissolved oxygen is going to drop in the water? And that's going to come from measuring the level of nitrate. Nitrate is basically nutrients, and a large reason why we have nitrates running into Galveston Bay is in the springtime when people are using fertilizer on their lawns or in their gardens, that extra nutrients or fertilizer is going to get washed into Galveston Bay. And what that's going to cause is an algal bloom. So that algal bloom is going to grow and use up that extra nutrients in the water, but eventually it's going to run out of that nutrient source and bacteria will come in and decompose the algae. And with the bacteria doing that, it's actually going to use up the oxygen in the water. So let's go ahead and see if we have high levels of nitrate in the water today. So for measuring the nitrate today, we're going to see another chemical reaction, and it's indicative of the color change that we're going to see. And so for this, it's actually a zinc reduction method. So we're going to get to play around with several different components today. The first thing that I need to do is get 15 milliliters of water. So I'm going to go ahead and get my sample. And again, it looks like I have a little bit too much, so I can just tap until I get to 15 milliliters. Right now I'm at 20. And now I'm about at 15. So the next thing that I have to do is take my zinc, which is in a little foil packet like this, kind of like a little packet of flavor for ramen noodles. You're gonna open it. And then we need to dump the entire contents of this into our reaction tube. And then after that, we're gonna put the cap on it and shake vigorously for about 3 minutes. So the next thing that I have to do is add 10 drops of acidifier solution to my sample cup. So this is basically an acid, so I have to be really careful not to touch my skin. So I'm gonna go ahead and add 10 drops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? And the next thing that I'm going to do is take my reaction tube that we just mixed up our zinc in, and you can actually kind of see some of that zinc down there at the bottom after our reduction happened. So I'm going to go ahead and add that to my reaction tube, and I'm going to be really careful not to transfer any of that zinc over to my sample cup. So here we are, we have another ampule this time with a different reaction liquid, and we're gonna maybe see another color change. So remember, I'm gonna put our ampule in the bottom of the sample cup, and I'm going to snap the tip, and now it is filled, and I'm gonna invert it several times so that the bubbles in there can mix it. And this time we actually have to wait for 10 minutes before we take a reading. So now that our 10 minutes is up, we are able to compare on our comparator scale where our nitrate level is, and I would say it's a little bit darker than 0, but it's not any darker than 0.3, and that in our units for this is parts per million as well. So there's not any more than 0.3 milligrams of nitrate per 1 million liters of water. So that's a really low level of nitrate. One thing that we would see that would be indicative of high levels of nitrate is if we were to see an algal bloom right now. And that would be because of that, remember, that extra fertilizer that can get washed into the bay, which would cause an algal bloom. So I would say that our nitrate levels are at a good place, and that means that we wouldn't have any drop in the oxygen in the bay anytime soon. So the last thing that we want to measure is the pH of the water. The pH stands for potential of hydrogen. So depending on how many hydrogen ions are in the water, it can change the pH. And when measuring the pH, it's anywhere from a 0 to 14 scale. So if a substance is 7 on the pH scale, that would be right in the middle. That's a neutral substance. So it's neither acidic or basic. An example of a neutral substance would be tap water. Now let's say it's on the lower end of the scale from 0 to 7, and that would be an acidic substance. So things that are acidic are like stomach acid, or maybe citrus fruits, and even sodas as well. On the other side of the scale, however, anything between over a 7 and 14 is something that's basic. So basic things are soap and bleach as well. So those are a little bit higher. seawater tends to be somewhere around 8, right? So that's a little bit slightly basic. But what we're finding over time is that the ocean is becoming more acidic. So our pH is starting to go down. And the reason is because of climate change. So with climate change, of course, humans are burning fossil fuels that is putting excess carbon dioxide and other greenhouse gases into the atmosphere. When carbon dioxide sinks into the ocean, it's going to change the chemistry of the ocean and cause it to become more acidic. And that's going to affect marine organisms that have a hard outer shell made of calcium carbonate. And those organisms can be things like oysters and clams and scallops and lobsters, and even corals will be affected by the changing chemistry of the ocean. So it's really important to know where our pH stands. So we'll measure that.
I dipped my piece of litmus paper in the water sample for 3 seconds, waited for it to dry, and then compared the color to my pH scale. The pH of Galveston Bay today is between a 7 and 8. Thank you so much for joining Artist Boat to take some water quality measurements of Galveston Bay. We hope that you learned a lot about how important the health of Galveston Bay is and what factors can change the water quality. We hope to have you out here exploring the bay with us soon.